welcome to this, our first session on the Python programming language. And this one will focus on creating libraries of Python code that you can install, that you can share, and we'll sort of see how deep we get into various aspects of this sort of sharing code. If you're here, my assumption is that you've programmed in Python, maybe you've done some data analysis with Python, you're sort of familiar with Python libraries that we use for data analysis, and they're sort of comfortable with Python. And I'll also assume, although that might be wrong about some of you, that one of the questions that you're asking yourself, and this is a question I get a lot from people that I work with, is, well, I'm doing all this Python in Jupyter notebooks or in scripts, but I'd like this to be better organized. I'd like my programming practice to be better organized in a way that I can start building larger libraries of code that I can reuse, that I can test properly, that I can install on various machines that I'm working on, that I can share with others, that I can collaborate with others on, kind of like start building tools that are more robust. And I think that kind of transition from here's my script that does some things that are useful to me to here's a library of code that I can share and collaborate with. That transition I think is a little mysterious and not often documented. And the purpose of this lecture and this tutorial is to kind of walk you through and try to demystify that. Along the way, I'll talk a little bit about some of the ways in which Python works in order to help you understand what Python does when we type import numpy as np. What is going on there? And could I also write import my library as ML and then keep on? And that's kind of the goal here, is to get you to that point. Okay, so we'll do all this on the hub. So you're welcome to follow along on the hub. If you haven't logged into the hub yet, it's neuroacademy.2i2c.cloud. And if you type in that URL and let GitHub authenticate on your behalf, and you should eventually end up in something that looks like this. And then we'll work mostly, one of the ways that you can view things in here is by clicking on this plus up here. That opens what's called the launcher view. In the launcher view, we can launch Python notebooks, we can launch Python sessions as consoles, but it could also launch a terminal application. And this terminal application is, I'll make this a little larger so it's a little bit more visible. Is this good? Can you see back there? Yep. This is the Unix shell. So just to explain a little bit about the hub, every one of you, when you open this hub, you're dropped into, we call it a pod. That pod is your own self-enclosed environment. And within that pod, you're sitting on a Unix machine that's running, I believe it's running the Ubuntu operating system, a Linux operating system. And we all are actually called, if you type who am I here? Sorry. Who am I? We're all Jovian. The Jovians are the inhabitants of Jupyter, so it makes sense that if you're in Jupyter Hub, you're Jovian. So that's the username that we'll all have. And later, when we talk about Git and GitHub, we'll talk about how to configure it so that it knows that it's you and not Jovian typing in the commands. But for now, this is what we see. And then if you do standard Unix commands, you'll see I have some stuff that I've downloaded into here. And you should all have this shared folder that contains data that we'll use later on, and we can use in order to share data for the hackathon next week. And there should be a curriculum folder. There isn't actually a folder in the curriculum folder for this session. I'll explain in just a second where we find the curriculum for this session. So you should be able to see all those things, and then we'll start working here when we start working. Okay. So the materials for this session are actually going to be found in here. I'll post that to Slack. This is, so It's on a website, neuroimaging-datascience.org. I'll show you what this looks like on the front page of it. It's Holly Arconi and I, after doing Neuroacademy for a few years, wrote a book, and the book is like a piece of dead trees that you can purchase, but also all the content of the book is also on this website. So I'm going to use this website where all of this is available for some of these sessions, because the materials are already there. And so we're going to look at chapter 7, which I also put the link. And we'll sort of go over some of what's in this chapter, and we might deviate from it a little bit, but I'll use this a little bit as in my anchor for this. So let's talk a little bit about sharing code with others. So the purpose of this is to make you kind of reach a point where you can share code with others. What should be shareable? So we write in my day-to-day life, and I imagine yours as well, we all write lots of code to do various kind of one-off analyses, and then we do some analysis and we think, oh, this is pretty good. I want to use it over there as well. And I think at that point, we start building maybe libraries of scripts, or kind of there are various solutions that people come to. I think not everything needs to be shareable in the sense that we will share it today. I think Jupyter notebooks are really, really useful as a way to tell a story about a particular data set, about a particular analysis that you did. They're really kind of useful. Just out of curiosity, raise your hand if you sort of use Jupyter notebooks like once a week at least. Okay, a lot of you do, but not everyone. Yeah, so they're fairly popular tools for sharing data analysis. And so you might have something like this in your life. I'll make this larger too. Here's just an example of something that I might typically do. I import some functionality from some Python libraries. I read some data from a CSV file, and then I do some calculation. I extract something, and then I do some kind of calculation out of that. So for the purposes of this tutorial, the premise will be that we're looking at some blobs from MRI data that we have already stored in a CSV file. We have the radii, and we want to calculate things like their area or their circumference, and report those, maybe write them out to a data frame. So the calculation itself, of course, is very simple and not too interesting. But this might look, if you're using Jupyter notebooks, this might look familiar to you. This kind of interweaving of reading of data, doing some computation. There's no visualization here, but typically there might be some kind of visualization of what we're looking at, and then writing out something to a file that we will use later for something else. And that's all pretty good, but it violates sort of a few ideas about good software engineering. In particular, the computations are embedded in here. The calculation itself, the math, is right in here, embedded among multiple other things. So we're doing two different things here right next to each other, and that's non-modular. There's also not what's called a principle of software engineering is separation of concerns. Separation of concerns is the idea that we do different things. We want to separate them from each other. For example, interactions with the file system, like reading of data, writing of data, those should be separated from calculations. Data management things should be separated from calculations. So all these things should be separated. That's sort of the idea, general idea of separation of concerns. Of course, again, this example is really, really simple. You look at it and you know exactly what's going on, but you can imagine that you're doing something that's a lot more complicated. Things start getting out of hand. I can imagine you have some examples in mind. I certainly have things from my life that look like they just grow out of, you start something and then it grows out of hand, and you need to do something. So this is not particularly reusable, right? Because we wrote some calculation here. Maybe this is some really interesting math that we came up with, and we can't really reuse this anywhere else because it's kind of locked into this Jupyter. So let's start working with this code and kind of think about how we refactor it. I'll create a Jupyter notebook. Actually, I won't create a Jupyter notebook. Instead, I'll move on and show you how we isolate these and rewrite them as functions. So the first thing that we might do in order to kind of refactor this code in order to apply a little bit of modularity and separation of concerns is that we rewrite the math itself as functions. So the first thing that I typically do when I'm starting to work on this kind of thing in a Jupyter notebook is that in the Jupyter notebook itself, I'll take code that looks like this, and I'll start rewriting it as functions. So that's a really good first step towards modularity, is to define functions at the top of the notebook and then use the functions later on. One of the benefits of this, that immediately these calculations can be reused multiple times within the same notebook. So if you're doing the same calculation again and again, you don't need to copy and paste this bit of code. Instead, you have a function, and that function can be reused. So this is, for those of you not familiar, this is the syntax to define a function in Python. The def keyword says that the following block is going to be a function, the name of the function, then there are arguments within parentheses, colon, and then in an indented block, we might have some computations and return statements like this, return the results of the computation. And functions can have more than one return depending on the logic within the function, and they can have no returns at all if they don't need to return anything. So now we've separated a little bit. We have like the block of code that does the computation down here, maybe some data management. And then the next step that we might do is that we might take and separate out the functions into a separate file. So this is something that I'll often do in my projects, is I'll have notebooks with computation, and I'll have many of them because I'm doing multiple things on multiple days. Over the years, I've struggled with how to keep this organized. Nowadays, the convention that I usually use is the date in which I started writing this notebook, dash something that explains what this notebook does. And then inside there'll be like a bunch of things. If I end up writing some code that's useful like this, and I think, oh, this is something that I might want to use in another notebook, I will create a .py file. For example, for this case, I might create, so let me go ahead and do this now. This. Make their my project, we'll call it my project for now. And let's say that I have my notebook in here. Let's go into my project here. This view of the file system, it refreshes automatically, but if it doesn't, you can also hit this reload and it'll kind of come up to date. So inside of my project, maybe I have a notebook with some computations that looks like this. And maybe I rename this thing, as I just told you, 40730 blob calculations. So that's the notebook that I'm working with, and I won't run this because it won't work because we don't actually have data called input data blob CSV here. But if I ran this, that would do that. It would define these functions. And then the thing that I'll typically do is right next to this thing, I will create a Python file. So clicking down here, I can create a Python file. It's called untitled, but maybe I'll call it blob functions.py. Oh, you know what? Better, I'll just go ahead and call it what I want to call it in the end, geometry. Because these are geometric calculations, I can take the functions that I've written and I can copy them into geometry .py, and now I no longer need the I do have from math import pi here, and that gets used inside of these functions. So I will also move my from math in here. And let me comment out this code here. run this from math import pi. So this defines these functions such that I can run them, for example, calculate area 1. So that does what you might expect. It calculates the area of a circle with radius 1. But now I've the first thing that as I said, the first thing that I do is these are functions that I might want to use tomorrow on some other calculation. So I remove them from here and I move them into geometry, including whatever import those functions require. And then what I can do now is I can restart the kernel here. So there's in the Jupyter Hub, there's a kernel menu, and if I type restart kernel, it restarts the state of the kernel, and I can remove this import, and instead I can say from geometry import calculate area, calculate circ. And kind of interestingly enough, that works as well. And so first, just to say something about the import statement. So when we import something, when you type import pandas as PD, or from geometry import calculate area, Python goes through a series of, it looks in a series of different places for something that would register as this name that we're trying to import, or this name that we're trying to import. And the first place that it will start is in the present working directory. So if we're sitting right here with this notebook, right in this directory, and there is a file called geometry sitting right there next to this notebook, it will try to import that file. In fact, we can also write import geometry as geo, and that would work just as well. Then geo contains now contains the calculate area function. Right? So that came from this file here. And so now we've moved one step further in our process, in the sense that now I could write another notebook here, and I could write the same statement in that notebook, and it would use exactly the same code as in this notebook. And that's nice, because let's say that I learned that there's some bug in this code 2 weeks from now, I can update the code in one place, and it would apply to all the places where that code is being used. Okay, so that's sort of the first step in the process, and a lot of the projects that I work on personally start out like this. There's a bunch of notebooks. There's a .py file. In that .py file, there are functions, and those functions may be more or less idiosyncratic for that particular project. In that project, I might have data of a particular type that gets read in a particular way, and I might write functions that address that. So I can separate concerns as well by writing functions that do data management or do other things for me, like interactions with the file system or interactions with other systems, by writing other functions as well. And so the code in the notebooks becomes more concise and more focused on a specific thing that the notebook does. Okay, let me pause here. What questions do people have so far? Yes.
So is that file that we wrote geometry.py, is that considered a library, or is there something else that's needed to call it a library?
So technically, this is a module, a Python module. It's really a very, at this point, it's very, doesn't have a lot of machinery for Python to do a lot with it. When you type import geometry as geo, this file actually, I believe, gets executed top to bottom. And in this case, executing this top to bottom doesn't have any side effects. I can demonstrate what I mean by side effects by restarting the kernel. Oh, right. So it executed the file top to bottom, and along the way it hit this and ran the print. We'll call this a module for now. There are many names that sort of have similar: library, package, module, all these things, but we'll make at least the distinction between module and library. This is not yet a library. Okay, One more thing that while we're here, we'd like to do in order to clarify things is document these functions. Functions in Python can be documented with multi-line string. This is just this is the Python thing that after a function definition, if there's a string that immediately comes after the function definition, that string becomes that function's doc string. So we could say something like calculate the area of a circle. So I wrote this doc string in a very particular way. And the reason that I wrote it in this very particular way, and here every character matters, is that there's a specification, a standard for how we write doc strings. It is the NumPy doc string standard. Okay. DuckDuckGo. Find you some doc. This is the style guide for writing documentation for NumPy function and NumPy compliant code. So it's got a very specific kind of thing. Here's the doc string, and it has these sections. At the very least, it will have these sections for a function of this sort. There's kind of like a one-line description. You might have more here. You can write some LaTeX math in there if you'd like. You can do a lot of nice things with this format. There will be a section called parameters. Parameters are the inputs to the function. Under that, there'll be like a string of these dashes, and those have to be exactly the length of the parameters. And then returns, and again, string of dashes. Parameters, the name, space, colon, space. The reason I'm insisting on every bit of white space here is that this thing will be read by others, and they'll have expectations about where to find different things. So people you share your code with eventually will want to know, oh, how do I use this function? And that'll be documented in this doc string. But also there are systems that can take and automatically take this doc string and turn it into web pages, into PDF documentation. So if you follow the standard, you can use those tools in order to create websites that include the documentation in other ways as well. So following the standard up front helps you, it makes things more readable, because I, as a person who also writes this kind of code, I can look and I can say, oh, I know where to look for a parameters block or a return block and so on. So this kind of consistent documentation is helpful. And following the standard makes sense. Calculate the circle, and then copy and paste, changing the necessary word. Okay. This is also nice because if you're in Jupyter now, and I'm restarting the kernel here, you can now do things like use the question mark. Who here is familiar with the question mark notation in Jupyter? Okay, what the question mark does is if you put it after the name of a function that you defined, it will print the doc string of that function into the Jupyter notebook. So here we get the signature and the doc string, and so we get the help kind of for that function. So that's kind of another step forward towards making all this stuff useful. Okay, so now our notebook or our script would look a lot more like this, more concise. We import geometry as geo, we import pandas as PD, we read the data, we do the calculation, then we write out. Okay, So now we have a module with some code. Now we'd like to move more towards what we call a package. In the package will be a set of different modules, maybe lots of different functionality that all is enclosed within, is organized together, is packaged together. So in order to do that, we will move from the current structure that we have to create in our project a directory called geometry. And we'll move our geometry .py file into the geometry folder. And I think maybe I also renamed it there. Yes, circle. So now imagine that we're doing a lot of different geometrical calculations, and these geometrical calculations that we're doing here, these pertain to circles, but we'd like to modularize our code such that circles are in one file, and I don't know, squares are in another, and so on and so forth. So for that purpose, we'll go in here and we'll rename this file circle instead. So these are the functions that pertain to circles specifically. We have a package called geometry, and inside the package geometry, we'll start developing things for circles for now, and later we can put in things for spheres and polyhedra and so on. Now, in order to tell Python that this is a package, we need to add one more element. So now, I believe that if I try to import now, let me just try that out, but I believe if I try to do that now, it will not work. It'll say, okay, I can't, I don't know where to look. And so the next thing that Python does after it looks in the present working directory for a Python file called geometry is that it will look in the present working directory for a folder called geometry that contains a file called __init___.py. So you might have seen in various places these kind of weird files called __init___.py, and I will use from now on when I refer to this weird __ before and after a thing, I will just call it dunder to shorten all that. So that's the dunder init file. So I'll create a dunder init file inside of my geometry folder. And by creating this file called dunder init, like that, I have made this folder into a Python package. That really is all that is required, is that this file exists here. And so now this thing is a package. This won't work, but maybe somebody could guess why this won't work. Let's try to look at kind of logic of what we've done so far and think together why this isn't what kind of error this will. Any guesses about what's going to go wrong here? What have I broken in the meanwhile? Yeah.
Would you have to tell it to look for circle within geometry?
Right. So I changed the name. So if I'm trying to import from geometry, it looks inside geometry for something called calculate area, and I haven't really told it where to look for calculate area. And so indeed, I can do something like, I think I can do this. Well, let's see first how this fails. Right. So I know so it's telling me, I know there's a thing in here that's the package, but there's nothing called calculate area in here. So we haven't told me where to look. And I think we can fix that by doing from geometry.circle. And that does work. Another way to kind of fix that is to think a little bit about what's inside of the init file. So now the logic is the following. When I type import geometry, when I'm sitting in this notebook and I'm saying import geometry, the dunder init file gets run top to bottom. And so inside the dunder init file, I could put all kinds of things that will sort of instantiate what I'd like to instantiate. For example, I can type from, I believe from circle import calculate area, calculate circ. So inside of the dunder init, I'm telling it this is sort of a convention to say in this folder, look for something called circle, and from that thing called circle, import these names. And so now I think that this should work. What has happened? Let's see, maybe I'm wrong about this convention. Let's maybe I haven't saved that file also. That could be. Save that and then restart this kernel. Yeah, right. Yeah. So I'm telling it, run this file for me. This file imports in turn from Circle these names, and it populates what's called the namespace. So the namespace of the package, the namespace more generally is in a Python process, more generally, the namespace is all the names that are defined within a particular process. So the namespace includes, for example, the name PD that then points to the pandas library, but also it might include, if I'm writing some code, radius equals 1, it will include the name radius in this case for this Python process. What we do in the dunder init file is we define the namespace for the geometry package. And what we tell it is bring into this namespace these two names, calculate area and calculate circle, or calculate circumference from this circle file that I have right. And I can do other things. I can define, I don't know, from math or pi, and then I can do, I don't know, pi squared. Pi. And then those things will also get defined, and I can, for example, import pi squared from pi. Okay. So that entire file gets, so you can put lots of different things in here if you'd like. Okay. So now we have a package. It's called geometry. It sits inside of my project a little awkwardly, but there it is. And I can develop it more. I can write other modules in here. I can import things from those modules in here. I can make this a lot more complicated. What questions do you have at this point about this structure? Yes.
Why would you put pi squared in the index line?
Oh, I guess I could put all of this stuff in inside of circle here.
I guess my question is
Why would we have anything? Why would we have anything defined here? Sometimes you want this kind of package level constants that are used everywhere, or maybe whenever you import the package, you want to do something else. I don't know, set up something in your file system in a certain way. You can do, or you can write arbitrary Python code here. It was more to demonstrate that we can run arbitrary Python code in here. Sure. That every time you do the import, that Python code gets executed. So if there's something that you need to set up for your library to work, that gets instantiated on import. And often, if you sit there and you're like importing some library, and then you sit there for a few seconds, that might have happened for you if you're running large libraries, large complicated libraries, is because they need to do all kinds of setup once they're importing, and that happens here, or it might happen inside of the definitions of various things that you're importing. Yeah.
Is there any way to automatically update this init file? Like if you made another script and you essentially my script, you just have to go back and remember.
Yeah, you have to keep all this consistent yourself. There's no way to automatically tell Python to update things as you're updating. Yeah. Okay, so we're one step further here in setting this our package up. So we're sort of here in this kind of thing, and now we can do things like from geometry import circle, calculate area, blob radius. It's And you can do that, again, you can do that in if you're here in this project and you have multiple notebooks, all of them can do this same thing. And like I said, you can make this package more complicated. Okay, the next step for us is what if we're writing something that's really useful, and it's not useful only in this project, but it's useful across a broad array of projects, right? Often, and this happens to me, I'm working on multiple different projects and they all thematically use similar tools, but they're working on different data sets or they're working with different sets of collaborators. And I'd like this set of functions to be available to me in all of these different things. So now what I'd like to do is I'd like this code that I wrote, this geometry package, to be in one central location and available across multiple different contexts. Now what I have to do is I have to put it in a place where, Python usually puts its packages. And so now what I'm going to do is I'm going to show you, well, if Python can't find a file called geometry.py right there in that directory, and it can't find a folder called geometry that contains a dunder init file, the next thing that it will do is it will go to what's called the Python path. That's a variable that's defined it's defined in the shell and defined for Python itself, and it defines a search path. So it's a series of file system locations, and it will go kind of like from top to bottom in these file system locations, and it will look for packages in those file system locations instead of looking in the present working directory. And you can see where that is. I think it's import sys print sys dot path. So sys is a standard library, a module in the standard library, and it manages things like the Python path. So you can see in our case, this is where it's going to look in the zip file. Then it's going to folder here, which is in some location. We're using the Conda package manager that some of you might be familiar with in order to manage the dependencies that are installed in this environment that we're working in. So first it'll look in some environment called notebook, and inside there it'll look for packages in this folder, and then it'll look in this place, and then it'll look actually in this libpython 310 site packages. So we'll go one by one, and it'll look for something called geometry, for a package called geometry. I think either a Python file called geometry that's placed in one of these locations, or a directory that contains a dunder init file in one of these locations. So you look at this and you say, well, let's just copy our file or our package right into one of these locations. And I'll say, slow your horses, because that is the road to a big mess on your machine. Instead, what we'll do is we'll use Python machinery, the Python packaging machinery, in order to install our package into the correct location determined by Python itself. Python will sort of do the installation for us. So now we need to organize ourselves a little bit differently. We're pretty close already, but what we need to do is we need to add to the package that we've created, we need to add additional machinery that manages the installation. And there's various ways of doing that. The currently kind of most standard way of doing this is a file called the PyProject file. So now we need to reorganize our files in a particular way. So first of all, we've already determined that we will want to use this geometry outside of just this project. So maybe we'll move it out to some other location. I've created in my home directory here a directory called source. That's something that I do on many machines where I'm working, where I put source code. Source code is code that I've edited or code that I've gotten from somewhere else. It's sort of a place where I put source code, and maybe I'll create a new folder in here and I'll call it geometry. And then inside of this geometry folder, so I'll move to source geometry, and inside of this geometry folder, I will replicate the file system structure that I have here. I will do all the things. I will touch a file called license. We'll come to that one, back to that one in a little bit. I will touch a file called readme.md. We'll come back to that one too. The Pi project, which I just mentioned, Pi project, and this file has the extension TOML. I think it stands for Tom's markup language. I think it's Tom. Strangely, it's a markup language. We'll look into what that looks like in just a second. And then within this, kind of by convention, we make a directory called source. And finally, we'll make another directory that we'll keep around called tests. We'll go back to that one in a little bit when we're ready to test our code. But for now, inside of this src source directory, we will place our package. So we will move from my project geometry. Let's see if this works, into source. Okay. And so now inside geometry, I have source, and inside that I have geometry. Inside that I have my init. And so I have inside the source, I have a package. So this is how I've sort of organized the code. And you could put inside the source, you can actually put multiple packages to make things really complicated if you want. Inside each one of these packages, you can put multiple modules like circle and square and so on. But this is how we fundamentally organize our Python library. So this is now we've gone from a package that had a module to a library that has a package that has a module. Okay, so this is yes, ls star. Yeah, it tells us what's in there. Okay, so I've organized it in this way. Now I need to set up everything for Python to know how to sort of handle the installation. And I've created this Pi project, minimal Pi project file in advance. We'll go over all the elements here. Let me put that inside of my Pi project TOML. So a few words about this. This is a relatively new system for installing Python packages. Those of you who've worked with source code in Python might have seen other kinds of files like a setup.py file. Has anyone ever seen a setup.py file? This text here, this chapter had setup.py in it until just last week when I updated it for today, because it's really a recent change that we have this Pi project file. The reason that this Pi project file exists rather than the setup.py is that there are now, for Python, there's a lot of complexity in how we package things. And so there are multiple what we call build systems that can build Python packages. And there are multiple what we call front ends or installation systems. Today, we will focus on one build system and one installation system. The build system that we will depend on here is setup tools. Setup tools is in sort of an older, more kind of traditional way of doing things in Python. It's existed for a long while. And if you've seen setup.py files, setup tools used setup.py in order to install. So everything in setup.py was tied to setup tools. And so here up front, we declare the build system that we are going to use is the setup tools. And maybe later in your life, when you're building really complicated things, maybe it will be advantageous for you to add additional build systems or other build systems. Just know that that's why this block is here. But for now, if you're writing Python code, kind of standard Python code, like the one that I showed now that doesn't have extensions in other languages or things like that, this is totally reasonable to do. We can specify also what version of setup tools, and it's good practice to specify what version of setup is required to build this, and we set that to a pretty high bar in order to be up to date. The way the syntax of the syntax of TOML works is that it's, you can think of it like a Python dictionary, where the keys are these square bracketed strings, and the values are themselves can be thought of as dictionaries as well, where we have variables that define, they can define things like lists. This should read a lot like Python code, with the exception that there are these square bracket titles for the different sections. And the Python installation machinery that we'll see in just a minute, it knows about, it knows how to read this. It knows kind of what this means when we say project, what it means when we say project.urls and so on. And what this file defines is it tells the installation system, it tells Python and generally what build system we're intending to use, but also specifies certain metadata about the project and certain, it's hidden here below, certain required data about where we might find packages inside of here. So this is how to find the packages inside of the project, your project URLs, like where we might find information about this. This is kind of all defined in this, and this can get more complicated. And this is about as simple as it gets, unfortunately. So let's talk through kind of the different things. I've already described what the build system section does. The project system, the project section defines metadata, things like the name of the library. You can put in a section on authors, and you can add, in this case, I've added just myself as an author, but you can add additional, this looks like a lot like a dict, so you can add additional dictionaries with additional authors. There's a short description here. This short description, maybe like a single sentence that can tell you what this thing does. And then you can define a README. We'll come back to the README in just a second to look at what we should put in there. But in this case, it's this file that we already created called readme.md, which uses the Markdown extension, the Markdown format. These classifiers here are standardly defined classifiers that then, if we share this package through, for example, or this library through the Python package index, which is a big website that contains, or an index that contains many Python libraries, then it could get classified and tagged and associated with other things that have similar classification. These classifiers are classifiers that I typically use for projects that are open source projects that have as their intended audience scientists, right? So in our context, this is, the topic is scientific engineering. That's kind of a good place to put this. It'll get classified together with, I don't know, other neuroimaging libraries. So I don't think there's something more like intended audience neuroimaging researchers, but science research is close enough. And then this here tells something about the license that we're using. And we'll come back to the license a little bit, but then it'll get aggregated with other things that are open source and licensed under a particular license. So those are these classifiers. We tell it what version of Python is required in order to run our code. In this case, I'm setting this to be larger or equal to 3.10. That's a pretty good place to put it these days. I think you can do as low as 3.8 and as high as 3.12. 3.10 is kind of, I think, the major one, and actually the one that's installed also on the hub right now. And then you can tell it my dependencies. I will have software dependencies, and this could be a list. It could be a pretty long list of dependencies, other libraries that are required in order to run your code. So far in our code that we wrote so far, we have not included anything that requires pandas, but let's say that at this point we're anticipating that maybe we'll want to use pandas down the line. In fact, in our code, there are no, if I remember correctly, there are no external dependencies. The math is part of the standard library, so nothing needs to be installed. That's already installed with Python. But let's say that we imagine that we'll need pandas in the future in order to install this. So here's where we define the dependencies. It's not a bad idea to pin the dependencies. Pinning means specifying the exact version of the particular dependency that you'll need for this. And this helps manage these dependencies relative to other libraries. It tells people, if you're trying to install this together with other things, you need this version of Pandas. It works with this version of Pandas. And then the next thing here is the version of the software itself. So at the point that you're creating a library, now you need to start thinking about versioning the library and maintaining versions of the library as well. Later on, we'll talk about how you can release this library out to the world for other people to use. For now, it's just not a bad idea to maintain versions so that you know, oh, I did this analysis with this version of my code, and then incrementing these versions as you make changes to the code that are significant, that there are meaningful changes. Here I follow something called semantic versioning. Oh. Really, you're gonna ask me to find ducks every time? Okay. SEMVer, or semantic versioning. This is like a snake eating its own tail, because this document that describes what semantic versioning is, versions using semantic versioning itself. So this is version 2.0.0 of the document that describes what semantic versioning is. This is a really important a piece of knowledge. It's a little obscure and arcane, but the thing to know is that if you're looking at versions of different software, like 2.2.2, the 2 that's leading here is the major version of the software. This is the minor version, and this is what we call a micro version. And where you made changes tells you a lot about, so if we went from 1.2.2 to 2.2.2, we know that some major changes happened to the software. Those 2 pieces of software, 2 and major version 1 and major version 2, might not be compatible with each other. Like code that you wrote for version 1 of pandas, major version 1 of pandas, will likely not work with major version 2. So this is a way for us to communicate with users, with other people using the software, about major changes to the software. If we've incremented the major version, that means we're going to break your code that used the other version. Think carefully before you update your code. But a micro version might be we fixed something small. A minor version might be we added some features. And if you want more details about exactly how this communicates, there is apparently plenty to say about that. Not that much, but so we're using this kind of idea of semantic versioning here, and we're setting the version now to 0.0.1, this to communicate that we're only just getting started here. Then I've added some project URLs to some URLs on GitHub. Alex, I see your hand was raised. Let's see if, do you want to just go? Hey.
Hey.
Oh, I can hear you sort of, but not through this owl for some reason. Let me adjust. Let me do one thing before sharing. Okay, never mind. Go ahead. I think I can hear it.
Testing. No luck.
You're in the room, so maybe if I do this. Go ahead again.
Testing. No?
Yeah, that's good. Go ahead.
So I was just wondering, this is a thought on versioning and software tools. I've been thinking about for analyses. I was wondering if you did or you knew anyone, for like pandas or other packages. Of course, it's tested on latest and stable and different levels of versions, from recent history. But I haven't seen anyone doing those for analyses to know when your analysis, needs to be updated. Do you know anybody that's working on that?
Right. So I think the question is, I have some analysis that I'm doing, and I'd like to be sure that this analysis works, with different versions of different software. And the question is, how do we sort of do that? And we can do that. I'll probably later today, when I talk about GitHub collaboration on GitHub, I'll talk a little bit about continuous integration, where we can kind of specify multiple machines that have different versions of different things. It's very standard when we write libraries like this. If we require Python 3.10, we would like to test it on 3.10 and 3.11 and 3.12, just to make sure that everything works across all these different versions. And you can do that for analysis code as well. I wonder a little bit if that's, for most analysis projects, that's probably overkill, is my guess. But
yeah, for
you have
sure.
something
I think one of the things that would be nice is if it, if you were pinning all your versions and you were maybe updating it, then you could pin to newer versions regularly. If this was still an analysis that you were using, sometimes I think one of the difficulties is it's hard to tell, is this something somebody wrote 4 years ago and hasn't touched since, and if it's still going to work. But yeah, point taken for sure.
Yeah, I'll just kind of divert here to something else. It's not a bad idea when you have these kind of projects like this one to place inside of here something that specifies the requirements together with their versions. So you could have, if you're using Conda, which is this package manager that we're using here to manage the hub and its dependencies, to have environment.yml. This is the format that Conda uses in order to manage its dependencies, and then have like an environment file that defines what was the environment together with all the dependencies that I used when I ran this analysis. And here are all the versions also. And then kind of put that together with your analysis code. The nice thing about that is that anyone using Conda can now download your code, say from GitHub, revive that same environment, and get those same software dependencies. So in that sense, your analysis is reproducible, even if not, for example, not transferable to a newer version of Python or a newer version of one of your other dependencies. So it works as it worked when you ran it, and may not work when you update. I don't know, if somebody fixed a bug somewhere and updates to some other, then your analysis may break and no longer be reproducible. So that was a little bit of a diversion from the central theme here, but I think still useful. Yeah, Tamas.
Hello. So I'm trying to figure out what we're doing here in PyProject.toml. Is it the same that Conda is doing when we ask it to create an environment with a bunch of stuff in it? Like, are we doing exactly the same thing? So this is like interchangeable. I don't need to do any more Conda stuff if I just nail this thing down.
No, unfortunately not. But let me I think this is an encouragement for me to maybe move ahead and show you, well, what do we do with this file? So give me another 5-10 minutes here, and then maybe your questions will already be answered. So let me move ahead here and show you how this is used. Then we can come back. If you have more questions about the content of this file, we can come back. Let me just finish with one last thing here about this file that I haven't described. So I described the version, project URLs are URLs that are relevant for this. And then this last section here tells us where packages might be found. And here we're saying we use the tool that is set up tools to find packages. So this is a long string of stuff. And we tell it where in this src directory, or we put the source, and we say include in, when you install this thing, include the package called geometry and anything that starts with geometry. So that's what this wildcard is here for. And don't include tests when you install this. So we'll have the tests together with our source, but don't install the tests in this case. And we can vary that if we want. We can actually, in here, we can say this can also be a list with the various packages or the various modules that are inside, or various packages that are inside of our library. So how is this used then? Let me just make sure that I have exact right. Yes. This is used in the following way. If we're in here, in our source geometry folder where we had all of this stuff organized together, then I can run python -m pip install dot. And what this would do is then use the pip installation front end. So we said there's setup tools, that's like the back end, the machinery for installation. And there are also front ends, and we're going to use the pip front end. Pip is the Python, what does it stand for? Python package, something about Python and packaging. I have that somewhere here. The package installer for Python. That's why it's pip, Python installer for Python. Package installer for Python. Pip. Anyway, pip is a short thing. It's used for installation. It's used in various ways. You can use it in various ways. So if I typed, instead of this, I typed pip install dot or pip install some name of some directory. And this is probably if you've used pip, who here has used pip for installing things? Some of you. So if you've used it, typically we're sitting somewhere and we're typing pip install, I don't know, NumPy. And that then goes to the Python package inventory and finds NumPy and downloads the right version and installs it. So it does that as well, but it can also be used in order to install from a directory. So if you say install dot this directory, it will look in this directory for a PyProject file or setup.py or some kind of thing that it recognizes as something that gives it instructions for how to install. They look in there, they'll see in our file, in our case, they'll say, oh, we're using setup tools today. Okay, let's use setup tools. Let's read all this metadata, set up things. Instead of doing pip install dot, I'm doing python-m pip install, and this is a good, safe practice to do everywhere that you're using pip. And the reason for that is, and some of you have used pip in the past have probably experienced the thing, you're typing pip install something, then you're doing Python and you're opening up your Python session, you're importing something and doesn't import, and that's because it got installed somewhere else in your system. And that's because pip may have been installed. The pip that you find when you type pip on the command line might be a pip that was installed under a different Python. You can install many Pythons on your machine. And so this guarantees that the pip that will get used is the one that this Python, the one that you call Python over here, has installed together with it. So this is a safe choice if the next thing you're going to do is Python run some script, because it's the same Python. So this is a good idea to do. And then Python-m, for those of you not familiar with this, the way to think about this is Python-m is a way to run a particular library as a script. So pip can be run as a library installed under Python, but also as a script that you can run when you do -m, and there are other, you'll see this in other places as well. So we're running pip, we're asking it to install something for us, and we're asking it to install the thing that's right here. And when we do that, it's going to look in here, find the build dependencies. And so it emits a series of messages. It says, oh, we already have pandas. We already have NumPy that's required by pandas. And then it'll go and it'll build the wheels for this thing. So it's building, in here, it's actually building a distribution of the code that you can then upload to other places in order to distribute this thing. But in the meanwhile, it sort of installs this version of geometry such that now all of that PyProject stuff has been instantiated in order to give us geometry 0.01, and it's installed somewhere. I'm not actually sure exactly where it put that, maybe here, but maybe not. We can verify that. So now let's just go back to our project and see that we can use this. So you'll see there's nothing here except for the notebook. So that's good. And if I restart my kernel here, I can now still run from geometry import so on and so forth. Oh, it can't import pi squared because I took that out of that init, so that doesn't work. But apart from that, it works. Okay, and now we can actually ask it. There's a way to ask import geometry dot file, and that'll tell us where it's getting it from, right? It points to where the dunder init file that it found as the package lives. Yeah.
So if you're building a package for library, and it has a bunch of like dependent other things like compilers and things like that, are you able to put that in and say like, please pull these 7 compilers and these files and these other projects off of GitHub and put them all under one project file?
So partial answer to that question is that when we ran pip install, you'll notice that it said requirement already satisfied and so on. If the requirement hadn't been satisfied, let's say that I added some requirement into the dependencies here, I had some requirement not yet fulfilled. I won't do this here, not to run into some issues, but let's say some other library that is required. During the run of pip, it would download that. It would try to pip install that thing from wherever it can find it, presumably from the Python from PyPI. And then update everything. If I pinned a version of pandas here, and let's I don't know, I'll get adventurous. If I specify a different version of pandas here, instead, it will, I believe it'll go and yeah, here it is, downloading pandas 2.2.1. It's saying Python, this is very particular, right? And we'll talk about this kind of thing in just a second here, because that relates to the other question. Downloading a very particular pandas 2.2.1 that works for my Python and my operating system here, and updates that. So now in the end, it'll tell me I installed geometry 0.01 and I installed pandas 2.2.1 because you asked for that. And I can just as easily undo that here. And so that's about the dependencies. But you're also asking about, well, what if I have some compiled extension code in here and I'd like to distribute that extension code? That gets complicated because extension code, presumably written in some compiled language like C, that is platform specific, right? If I can, Python, one of its charms is that I can give you some Python code that I wrote, say, on Linux, and on your Windows machine, you will happily run that so long as all the dependencies are in place and Python was compiled for Windows and so on. But for extension code, if I compiled it on this Linux machine and handed it to you and you tried to run it on Windows, that would not work. And so that complicates our life a little bit because now you have to find a Windows machine and compile there as well. And that comes back to these wheels. So a wheel is a format for packaging together a lot of things like compiled components and sometimes even like statically linked libraries and dynamically linked libraries. You put it all inside this one file called a wheel file. And you put that in PyPI. And then if somebody downloads that, they get everything together, packaged together, including, for example, compiled extensions. That file doesn't exist. What Python will typically try to do is download that code and then try to build it, as in try to find the compiler to compile this thing. Things can get pretty complicated pretty quickly. Yeah, other questions? Yeah.
So if I set up my environment with Conda and an environment of YML, and I want to like set this up on a new computer, whether it's on someone else who I'm sharing with, but then I also have my self-built package like our geometry package, and I mean that would not be part of any Conda environment, I guess, or maybe it would be. So I'm just wondering, like, what is the best procedure for after setting up the Conda environment that pip installing?
I have a ready to go example for this because our Jupyter Hub image, the image that we're using is this in this directory. So if you're interested in, oh, there's some question here. I'll come back to this question in just a minute. If you're interested in just how the Jupyter Hub is set up, we have here an environment.yaml file that contains all the files that are installed into the hub. So this is, I don't know, not too complicated environment file that you can share with somebody else for them to build an environment, just like the one that we have on the hub, for example. And the components here, so there's a section up here that defines dependencies. Make this bigger. These dependencies are dependencies that are installed by Conda, and it actually has some channels. It's using various places to get its Conda packages. But there's also a pip section in here. So all these things are installed by pip. And so there's various things that are installed from pip. And down here, you'll see the Crack encoder is installed directly from Keith's GitHub. And not only that, from a very particular commit on GitHub. So if you tell pip git plus HTTPS some Git repository at a particular Git identity, and we'll come back to that later today to talk about what these are, then it will go and it'll try to install that. It'll look at that place, it'll download whatever is down there, it'll actually clone this repository, and it'll try to run pip on that. And if there happens to be a PyProject file in there, or a setup.py as in this case, that'll just work. So you can give people, you can say, here's my GitHub repository with my library. Here's an environment file that points to a particular, like you can put here if you tagged, and again, tag is like a Git term here that we will explain later today. If there's a tag and you say, oh, put 0.01 as the tag, that's my version, then should work as expected. You'll have a very specific version of the library that you're developing. Okay, let me see what was the question on Slack. Let's say, I think I've written a few functions in Python that could be useful for broad everything related to this Python, but I want to turn it into a toolbox with a GUI. Can I still shoehorn it into a Python library? What is the point in the life of a library when the packaging you showed doesn't suffice? Okay, and then Michelle already answered some of that. There are some software tools that are Python libraries with GUI components, for example, Bitcoin. So there are cases, yeah, so you can imagine that things get really, really complicated here. One way to do this, and I'll talk about another way as well, is you have your source, you have your geometry, and inside the source, maybe you have like separately, you have like a library called GUI that implements all the GUI components for the GUI that uses this library. And you always want those things to go together. And what you would do then is you would create all this GUI stuff here, and you would create a little script that can be called from the command line that starts the GUI. Or maybe you'd create, like, if you get more complicated, something like a double clickable that calls a script that starts the GUI. And then you would have the GUI integrated together. It might, if you get to that kind of complicated use case, you might even consider separating the library and the GUI into two separate components, two separate projects, so that you can develop one and the other. GUIs and software libraries like the one that I showed you here with computations often have pretty different kinds of development considerations, life cycles. You don't necessarily want all the dependencies of your GUI to also be dependencies of your library at the same time. And if they're all installed together in one pipe project, it's hard to say. It's not impossible, but it's hard to say, oh, now I'm just installing stuff for the GUI, or now I'm just installing stuff for the library. So you might want to separate those two. But it gets a whole lot more complicated, and more complicated use cases you can handle those more complicated use cases with this machine. Yes.
While we're on this file, I did have I guess a splitting hairs question about the requires Python and the dependencies. Just kind of to clarify, so the required Python, the syntax is mentioning like you need at least 3.10 or higher, is I'm assuming what that's saying. In other words, like implying that if you get like 3.11 or 3.12, it would still work. Whereas with the dependencies, dependent and pinned to 2.2.2, is it still possible to use like a compatible, like assuming that like 2.2.3, for instance, appended is still compatible, would it still run despite it saying like equals particularly, or does it have to say greater than?
Yeah, so depending on how you're using it, it gets really complicated because depending on what you're using this together with and what those things require and so on. So in a particular environment, you might want to relax your pins a little bit, like do larger or equal to something. There's a lot more subtlety to that as well. Okay. Yes, I see, Thomas, I see your hand. Oh, forget.
Just piggybacking on that, so trying to understand, let's say that I felt very confident about my code. I'm going to go with the larger than sign. And 5 years later, Pandas decides to write deprecate a function that my code is using. Will I then get a lot of frantic emails that my package isn't working because it's gone? And somebody installed it with the new, with the latest. And
yeah, I think I'll broaden your question a little bit to like, what should we share and under what conditions? So I will hopefully address specifically your question, but let me broaden that a little bit more to like these two files that I already mentioned, readme.md and license. Those two files here are not files that the machine uses in any particular way. Those are files for other people to use, and they define the expectations that other people using your code. So the assumption is using this code, now we installed it on our machine. But in a similar way, if you put this code somewhere public like GitHub, now other people might download your code and use it themselves. And maybe that's something that you're interested in doing. Maybe this is for you and your collaborators, and you tell your collaborators like, like I showed in the environment, put in this version, and now we can run, we'll both be running the same analysis. I'll update the code, and then you'll update your version string, and everything will be in sync so that everyone that's working with you, you yourself, when we're working on different machines, will have a version of the code. But you might want to go one step further and share this code with the world. And if you put this code up, say, on GitHub, now there are certain expectations or certain restrictions that you need to sort of manage. So first of all, I'll just say, if you put something out there, if you put code up on GitHub, for example, and you do not include any license, then at least in the United States, that code is your copyright, and nobody else can do anything with that code without your permission, without your express permission. You own that code, it's your copyright, and if somebody goes and downloads that code and puts it into an app and then sells that app for millions of dollars, then you can go and sue them in principle. In practice, that is rarely practical for like the kind of stuff that we do. But that's what licenses are for. Licenses are documents that are sort of legally describe the rights of people who take this code and download. Here in this case, for example, I've pointed to this MIT license, and I'll go to open source. So this is a problem. Should really docs again. The open source initiative. So this was something that people recognized very early on in developing open source software. They realized that together with software, there are these kind of social restrictions and freedoms and things that we need to think about. And at some point, I believe in the 90s, people both in kind of the software industry, but also people in open source, sat together and started this open source initiative in order to define what is open source software? What is software that we put out there in such a way that other people can use it? And what falls under this idea and what doesn't fall under this idea? And one of the things that they did is they said, here are a bunch of licenses, a bunch of documents that you can use in your project, and they define certain rights and restrictions on use. And the MIT license in particular, so I believe there's a list of licenses here. There's a definition of what is open source here that you can look at. And B, you can say, I want a license that applies internationally, that maybe is popular. That will probably point you to something like the Apache license here, but there are others. You say, I don't want this to be reusable. Then there might be something else. Anyway, I'm just going to look for the MIT one because it's really simple. Here it is, the MIT license. So it's a document that we can just put on the screen in one time. That's an advantage. It's very short. You put in here, you say, my name in the year 2024, Ariel Rokem declares this is my copyright, and I'm permitting people to use this free of charge to any person who obtains this license in some way, and they can do anything they want without restriction. They can use it, they can copy it, they can modify it, they can merge it, they can publish it, they can do all these things with this thing. And they can also permit other people to do that. They can put it into their product and sell it if they'd like. I don't care. So long as capital letters, this is provided as is and without warranty. And that's pretty important. If you put code out there in the world and you give other people permission, something goes wrong, they put it into a medical device and something bad happens to someone, you don't want to hear about that. And also, I think this one also may or may not. In some cases, some of these licenses also include text about how they're not allowed to use your name in order to advertise any product, which might also be something you don't want people doing, right? I don't want somebody to be like, here's this medical product and it's written by these people at the University of Washington. Right? I don't want them to come back. So that's kind of the thing that a license includes. So this is kind of like a legal document and specifies the right that people have. And I tend to use licenses like this one, which are extremely permissive, meaning except for like taking liability, do whatever you want with this code. And I think there are benefits to that in the sense that now people can use this code in, for example, commercial products, and then those commercial products can do good things in the world, and that's awesome. And commercial products will come back and say, hey, this doesn't work the way I expected, here's a fix, and come and collaborate with me. And that can happen. I've seen it happen, so I know it happens. But there are other kinds of licenses. There are licenses that, for example, don't allow you to redistribute the code unless you redistribute it under the same conditions, right? And that would be a little tricky because if somebody else wants to put this in code that they want to sell, they can't make it open source in the same way. So there's a little bit of a distinction there. And that's in this license document. So that's one kind of social arrangement around code that we share. The other kind of social arrangement is in this other file called README. And that one is a little bit looser. So here's one example that I've written. This is markdown format. The reason to use this markdown format is that when we put this in GitHub, a place where we often share code, it gets formatted nicely on the GitHub web page. So this is it's kind of a useful way to do this. So I'm telling people what this is, and then I'm telling people, if you want to contribute, do the following things. And the README can get a little bit more complicated in terms of providing instructions for installation, providing instructions for use, and so on. But one important thing to do here is to communicate clearly to people who download what their expectation can be. And that's where I come back, I guess, to your question, which is, how do we tell people, well, don't expect me to come and fix your problems, or if you're installing this and it breaks, you can email me. In some cases, I develop open source software that I hope and want other people to use, and I want them to come to me and tell me when they have problems. So I tell them where to report about these problems, and I try to tell them clearly what their expectations should be about what level of support they should expect from me. And that depends a little bit on what you want to do with the software. If you want this to become a tool that many people use and is broadly used, then you need to sort of talk about these expectations. But that kind of depends on what your goals are. And so long as you communicate them clearly, that's fine. I'll also mention, if you become very serious about this, you should think about how you get credit from distributing the software, things like software citation, attribution, publishing papers that describe the software. You're very serious about writing software that other people use, and you want them to be able to give you credit for it. The coin of the realm in science is citation often, so making it easy to cite. One thing that you would want to do then is use a system called Zenodo in order to create a digital object identifier, because a digital object identifier is something that most journals will allow people to cite. And then if you get more serious about it, you might write a paper about the software that you wrote and then collect citations to that. And if your software is very widely used, then it will also get heavily cited, and that will be good for you because, like I said, the coin of the realm. Okay, what other questions do people have? Did that answer your question?
Yes, thank you.
Okay. Let me just do a quick foray here into software testing. You may remember that I put in there a test directory in here. And the thing that I'd like to say about tests is that is the place where we will put code that tests our code. Russ mentioned code testing. It is very important. I'll also probably come back to that on other occasions this week and hopefully next as well. Here, what I'll say is just that one thing that we might do is put inside of the tests folder an individual file that tests each of the modules that are defined in our package. And we'll call it, by convention, we'll call it test underscore name of the module. For example, here, test circle. Here, touch tests, test circle.py. And inside of that file, the thing that will go inside of, so it's in a separate, kind of like by convention of building this structure, it's in a separate folder, separated from the main implementation of the code. And it can contain code that looks something like this. So I'm importing the code that I implemented, and then I'm importing some other things that I need for my testing. And then I define a function that is a test function. So again, this has to be called test underscore something, and by pretty strong convention, it's called test underscore name of the function. So test, in this case, test calculate area, which is the function that we're testing here. We've imported it up here. We're executing it down here, and we're using an assert statement in order to assert the truth of a certain calculation. So in this case, we're going to try out a calculation. The test functions in general, what they include are a series of assertions or a series of executions of our code under different conditions in such a way that we can check that the result is correct. So in this case, we know that if we calculate the area of a circle whose radius is 1, the result should evaluate to pi exactly. And we can test that by here strict equality between these two things. The assert statement in Python has the following structure. It's first you say assert, then you have some statement that can evaluate to true or false, and then you can have like an error function, calculation. Right, so this will be the error message that will be emitted if this calculation did not work. For example, I don't know, do this just for fun. Now let's run this test. I'm going to use a test runner called PyTest here. And I will run it. So it's a command line app that I run. I test this thing, and it looks inside the folder where we run it. It looks for files that start with test underscore. And inside those files, it looks for functions that start with test underscore. And it runs all of them. And it keeps track of how many of them failed in various ways. How many of them raised errors, for example. Oh, that's not good. Okay, pip install. We'll add PyTest later to our environment, but for now, I'm just going to do that. So here it's saying, oh, something didn't work. And actually, you got also an error message, calculation did not work. That can be more informative. So I have to go and fix something. And then when I fix this thing here, then now it will go and test it, and now it passes. So it's kind of like the green-red method here. If you're doing test-driven development, trust mentioned, you start by writing the test. And when you first write it, there is no function, there's nothing to run here, so it will fail. Then you go and you implement your function until it passes in this way. So this is very briefly about testing, and like I said, we'll come back to this. But this is where you start building your library of tests, and as you're building your library of functions, you can also add to this library of tests more and more tests. You can add additional test cases. This is a test case, but you can think, well, if I had instead of calculate area 1, I had calculate area, let's say. Can add another case here easily. Assert calculate area 0 equal 0. Right, and now I have another case. It's in the same function, so it's only calculated as a single, but I can do, if I do separate functions here, I call it calculate area 0. Then now I'll have 2 points here. And it's kind of satisfying. You build your library, and then now if you have like 100 tests, it'll be like, it's very satisfying to watch as you're developing all your tests being run. So that's a little bit about testing. But like I said, we'll come back to that. But for now, what questions do you have about this testing mechanism? I went through it a bit quickly. Yeah.
I guess I have a question about like, earlier we like excluded the test folder. And now we're using like PyTest dot, and just like a little bit more about that.
Yeah, so the exclusion here was to say, if you're installing this on a user's machine, you don't need to install these tests, because presumably they're going to import this and use it in some other context. They don't need all these tests installed into their machine. So we have separately here sort of the development environment in which we are testing this, and installation environment where it gets run. we're almost at time here. Questions from Zoom? Oh yeah, I see your hand up now, Thomas.
So in an ideal world, we have a library with 5 functions. They would at least have 5 tests. And preferably more, the more my imagination can think of edge cases that can break them, and just write as many as I can.
Sorry, could you repeat that? I couldn't quite catch the end.
Yeah, so let's say we have a library with 5 functions. Should I write then at least 5 tests for each of them, and preferably more, if I can even think of edge cases to break them, as many as I can?
Yeah, as many tests as you can. It starts getting a little hard with scientific software though, because sometimes it's very hard to say what is the correct answer to a question. And also some of these things take time to run. And so you want the tests to be short also to run, so that you don't end up saying, well, this takes too long to run, so I'm never going to run it. Tests that you don't run are not very useful. So there's a balance to strike there, both in terms of the level of accuracy that you require, in terms of the answer, and also in terms of the runtime that this requires. So it gets a little complicated. It's not a bad idea to have at least what we call a smoke test for every piece of code that you have. A smoke test is a thing that makes sure that the code runs top to bottom. It gives you something about the result. Maybe the shape of the result is what you expected, or when if I gave it a time series with like certain dimensions and I did some reduction, like the average, then I got something that was reduced on the last dimension in just the right way. And I'm not going to check exactly that the values in every cell are the correct values. Does that make sense? Okay, great. Okay.
Just like curiosity, is there any equivalent to the assertion function that you know in R?
Oh, in R, yes, there is. In R, there's an entire library called test that does pretty much what PyTest does, and is lovely to work with. It's really, so yeah, I can do similar things. I actually, when I work in R, I've only recently started working in R. I'm a lot more careful there. I write a lot more tests before I do anything. So I've really enjoyed using test that. All right, I think we're at time here, so let's maybe stop here and we'll resume in 90 minutes after lunch.